for ideal gas. These laws we studied last session: Boyle's law, Charles' law, Galactic law, related to ideal gas. Boyle's law, which is PV equal PV at temperature constant. Charles' law, V over V, V1 over V2 equal T1 over T2. Same like this, it's similar, but I'd like to write it V1 over V2 equal T1 over T2. This at P equal constant. Galactic law is B1 over B2 equal T1 over T2. Also, I'd like to write it like this: B over B equal T over T. Direct proportional, same like Charles, but Galactic at volume constant. Last law, not studied for the first part, Avogadro's hypothesis. This Avogadro's hypothesis, it's happening when pressure and temperature both is constant. Pressure and temperature both is constant. When pressure and temperature constant, so the volume is changed with number of moles. Okay, and it's also directly proportional. So V1 over V2 equal N1 over N2, which N is number of moles. So at the end we have four equations: Boyle's, Charles, Galactic, and Avogadro's hypothesis. These four equations for gas studies. General gas equations. General gas equation, maybe we write it in different times when we solve the problem, when we studied or supported to study anything before. Here is the topic or the lesson for this one: general gas equation and variable for gases. BV equal nRT. BV equal nRT is the general gas equation. General gas equation. Other equation, it is BV equal mRT, but we have another one, BV equal mRT. But this R is not the same this R. This R here for number of moles, for the equation have number of moles. This R is universal gas constant, which is one value for all gases we can apply. But for other one, BV equal mRT, here R, it is not constant for all gases. This R value is specific for each gas. This R is specific for each gas. Each gas have R for each one. Okay, we can mention for this one R bar, R dash, this one RU, universal, whatever, but this is not the same as this one, according to multiply for number of moles or mass. Okay, this mass. How to convert from this one to this one? What is the factor or parameter control from this to this? We will see. We have something is called molecular mass. Molecular mass M, this one M capital is equal to M small, which is mass, this mass, kilogram or gram, and this number of moles, which is kilomole or mole. Okay, this what? This molar mass. The molar mass here is a factor control between or change from normal one or general one, BV equal nRT, to BV equal mRT. See what this happen? BV equal nRT. So this n I can replace by m by m. So BV I can write it like m by m RT, which is R here is RU, R universe, correct? So now we obtain the R, M, sorry, mass, converted from N to mass, but we have M molar mass. This one with this one, when we divide the universal one divided by molar mass for this gas, we obtain the R specific. R specific for each gas. So the R specific, where it's come from where is this one coming? From R universal divided by molar mass for this gas. That's it. Okay. Other equation here may be deduced, but important. We will maybe we use it for another problem. I think in exam 4, we use this equation to continue solving for the problem. What is this equation? You see PV equal mRT. correct? R dash. So what is the definition for density? Definition of density. Density rho is equal to mass by volume. So if I put the volume other side, so we obtain mass by volume, which is equivalent for this equation. Okay, we have mass divided by volume, so we can replace mass by volume from here and put it what? Density. So B equal rho R bar T. What is rho here? This density. From where is this mass divided by volume? Clear? This is important actually, used for some supported equation. We'll see in problem exam 4, as I said to you. This one support the equation to continue solving for the problem. Here, as you see, molar are universal. As we said before, it is one value for all gases. But here you see different values. Why you said me this one the same for all gas and different? No, this is the same, still the same. This is the same. This one, this one, this one. But the different only different units. Different what? Different units. But all refer to the same value actually. Same value but different units. Clear? Simple questions for gas, ideal gas equation, just to apply simple equations for that. Here, as you see, we have gas at standard pressure and temperature, STP, meaning standard temperature and pressure. And we have temperature 273 Kelvin and pressure 1 atmospheric. What is the volume for 1 mole of gas? So we need volume. At what? At pressure 1 atmospheric, temperature 273, number of moles. So to solve this one, to get volume, BV equal nRT, because we are given nRT. B is actually given, temperature is given, volume is required, number of moles is given. So what's remaining? R, but this R here for the equation have N, this one value for all the same. Okay, we can select it 8.31, but this is SI unit. When you check this here, I found this atmospheric, this Kelvin. So if I found R with value related to the units have atmospheric the same or something like this, it's better to use it. You don't convert any units. So we have R here, equivalent to another one for SI units. Liter, atmospheric, mole, Kelvin. So mole is okay, Kelvin is okay, atmospheric is okay. So what we obtain for by liter. So going here, substitute V equal nRT over B. All you have, direct substitution, get answer. Okay?
Doctor, R value, where did we get?
These are value for all gases are universal. If you check the previous slide here,
Okay.
here, this all, as I said to you, this is all the same, but different unit only.
For all
So
gases,
what the regular value 8.314 joule Kelvin mole. This is the regular one, but I use another one equivalent to this one. This value, which is liter atmospheric Kelvin mole, to change unit as per give. That's it. Okay.
so we need to know in which unit we need to know the value of R.
Bar.
We need to know the value of R in all the units.
To save value for all units.
No, this R value is same for all gases, all ideal gases, right?
For this R, yes, R used for this equation, one value for all gases.
Okay, and the unit, which unit we need to actually keep in mind?
I think it should be given, yes.
It should be given on,
save
right?
it, yes.
Okay.
Should be given. Other equations almost same are here is the same selected later atmospheric mole Kelvin, which is the same value, but here required pressure. When you read the problem here, we'll find the required pressure in millimeter mercury. See, millimeter mercury. But you can get it from here when you solve it by this units. I can get it by atmospheric. So after you get it atmospheric, we need to convert it to millimeter mercury. Here given volume 200 milliliter and given mass 0.12 gram. This mass temperature here by 35 Celsius. So sure, we change 35 plus 273 to obtain it by Kelvin. 200 milliliter should be changed to liter, and this 1 liter, it's okay, matched, mole matched, Kelvin matched. So the what you get, the atmospheric. But what's remaining actually the number of moles, because the equation is BV equal N
RT.
R universal T. Temperature is given, but need to change unit. R universal given. Pressure required, volume is given. So what's the remaining number of moles? But here he
Number of
mentioned for you the gram, which is referred to mass, and the type of the gas we have. So we can get it in by equation M over M,
N.
correct?
Correct.
This mass is 0.12, and number of moles should be given, molecular mass, sorry, should be given actually. But if it's not given, you can calculate. Carbon, normally carbon 12, normally for carbon 12, normally for oxygen 16,
16. Hydrogen 1.
normally for hydrogen 1.
1.
So
Yes.
CH4, calculated CH4, 1 from carbon, which is 12, plus 4 from hydrogen, which is 4 times 1, equal at the end 16.
16.
Okay, so we can
Okay.
get this 1 by 0.12 divided by 16 to get the number of moles. Once you get the number of moles, substitute in equation to get the pressure. After you get the pressure, you get it by atmospheric. So
Yeah.
you need to convert, just cross multiplication. Put the conversion. 1 atmospheric equal what? Equal 760 millimeter mercury. So what you needed from millimeter mercury here, this is required, equal what you
Answer.
obtain here
Ah,
for atmospheric one, for the new one, for the pressure, and just cross multiplication at the end, you can get the value required, which is equal this value you have, multiply 760 divided by 1. Okay, this
agree,
one?
sir. Okay.
Okay. Here we get at the beginning pressure 0.9459 atmospheric, and then after you get the pressure, you can get it what? Pressure with the unit new, which is, or unit required, millimeter mercury, as per this cross multiplication here, correct? This value, which is 0.9459 multiplying 760 divided by 1, you get the value direct. Okay,
Hmm?
okay, this equation. Just read it, and we will continue to solve it together. Finish reading.
A volume of our started.
Ready? Okay. Here, the volume of a bubble starting at the bottom of the lake at 4.55 Celsius increased by a factor of 10. So we have a relation between the volume 1 and the volume 2. So volume 2 equal 10 volume 1. This is given.
Mm-hmm.
Also, we given T1 4.55. Don't forget plus 273. And T2 18.45 plus 273. And the pressure at 1, sorry, is this pressure 2? I think so. Starting at the bottom of the lake, at increased by a factor of 10 as it raises to the surface where the temperature is blah blah blah. Yes, this pressure 2. Pressure 2 is 0.965 atmospheric. Determine the pressure at the bottom, which is B1. So we need B1. Here, what's your opinion? Volume change, temperature change, pressure change. When the three parameters change, the only way use the same equation ratio between total ideal gas with total ideal gas. Okay, like we consider the number of moles is not a change. We consider the number of moles is not a change. So the number of moles not a change and R constant not a change. So we can write it BV over T is constant. BV over T is constant. So I can write a ratio between BV over T equal constant, which is BV equal over T at 1 equal BV over T at 2. When we check this again, we will found I have a ratio between V1 and the V2, so we can get value. We have T1, T2, okay. We have B2 and the remaining B1. One equation and one unknown. That's it. Direct substitution. Easy? It's okay?
Yeah, it's okay.
Okay. I check here, we found B1 at the end. Direct substitution, and we get it by atmospheric, same B1, B2. B2 by atmospheric, B1 by atmospheric. You ask me, I can't substitute by atmospheric direct, no need to this
where from you took this PV over T?
Again, your question?
Where from you took this PV above T?
This from ideal gas. Ideal gas,
PV
BV
equal to
equal
nRT.
and here we can consider when the pressure and volume and temperature all is changed as here given. So we can consider the number of moles not change. Number of moles for the system you study is not a change, and also this is constant by default. So I can write it BV over T is equal NR, which is N is constant, R is constant. It means this totally is constant. So BV over T is constant. It means BV over T at state 1 is the same BV over T at state 2 is equal to BV over T at state 3 and so on. Okay?
Yes, clear.
Read this first also. Finish reading?
Yes.
This one is what questions? This problem is similar like previous problem, maybe different required, something like this. Here, child release of 6 liter helium balloon in a parking lot of museum. The temperature. Okay, firstly, write the given. T1 equal 28.
T1 equal to 2850 plus 273.
And also the air pressure, which is P1, 757.
MM of G.
2.2 millimeter mercury. What will the volume? So the volume is required here.
Yeah.
P2 is required. And the V1 equal 6.25 liter. What else? Another temperature here, temperature 2, minus 34.25
plus 273.
plus 23. The B2, 366.4 millimeter mercury. So the pressure is the same units. We don't need to change unit. This Kelvin, this Kelvin, so it's accepted. This liter, if you need to change it, it's okay. If not, no problem. We get it V2 by liter also. The same equation, BV over T equal BV over T. That's it. Direct substitution. Direct substitution. Any question, please? No question?
No, sir.
So we have a V proportional, inversely proportional with pressure, while is low. We have V direct proportional with T, the Charles is low. V with N, Avogadro's low. And from this package, we can get the BV equal N RT. Here we discussed this before. I talk about for the R gas constant for general all, and the R specific for gas. For example, R for air 287 joule per kilogram Kelvin. 287 joule per kilogram Kelvin. This R for air. Okay. I write it this value because this we use it a lot in the problem. The problem is coming with air is famous question. So R for air is 287. Here's this a direct apply for gas mixture. Direct apply for gas mixture. You remember gas mixture? Dalton's law. You remember Dalton's law? The pressure, the total pressure is equal to the sum of partial pressure for each gas. Correct? So
Correct.
this partial pressure for nitrogen, which is equal to 4.48, and this is the partial pressure for oxygen, which is 4.48, the same because it's the same value here. Apply, and you get the same final with the same answer. But at the end, what is the pressure for air, which is include oxygen and nitrogen? So we're going to direct multiply
270.
the first one and the second one. So it's 4.48 plus 4.48.
Mm-hmm.
That is okay. Start for some questions. Any answer?
1.
All agree for 1A?
Yes.
Or what you mean? A1, it means B? Okay, check chat. No, here specific heat of air at constant pressure is equal to 1. Number A is agree or not agree? Not agree also, no. Only 1 is okay. Specific heat at constant pressure. For air, this gas, we have 2 specific heat. So what's the meaning of specific heat first? Specific heat. This is the energy required.
Energy required to raise the temperature of
1 degree.
By 1 degree Celsius.
Okay, for
at atmospheric pressure.
Mass. For unit of mass. At constant pressure, it means pressure constant. At constant volume means constant volume. Here is specific heat. We have 2 specific heat, CB and CV, and this for gases only. But for liquid or solid, we have only 1 C. 1 C.
Come again, sir?
Again, for
Yes,
gases, we have 2 specific heat, CB and CV. Okay, one at constant pressure, one at constant volume. But in liquid and solid, we only have 1 C, 1 specific heat. Why? Mainly because for liquid and solid, for liquid and solid, the relation between pressure and the volume is almost not effect. So if you like a liquid incompressible, if you affect by a pressure, The volume is the same, not a change.
Okay.
Okay, but CB and CV is related for the gases, because I can use it as constant volume and I can use it as constant pressure.
Okay.
Why specific heat at constant pressure greater than the specific heat at constant volume? Easy. Specific heat constant specific heat capacity at constant pressure. Why is greater? Because the heat is added at constant pressure and substance expand and work. Expand and work.
Why specific heat at constant pressure greater than the constant volume? Okay. The heat capacity of constant pressure is greater than the heat capacity because the heat is added at the constant pressure. The substance expanded work.
This some value important. It's better to save it. Okay, but almost it should be given. But just to remember, CB is 1 kilojoule per kilogram Kelvin. CV is 0.718. 0.718.
That means air at 300 Kelvin. That means normal 300 Kelvin means around 1.2 degrees Celsius, right, sir?
Again,
1.2.
what is the degree of Kelvin? What is the Kelvin?
27.
273.
273.
273. So, is 0 Kelvin. Sorry, is 0 Celsius.
Yeah, it's 0 point something degrees Celsius. Yeah, right. Okay.
I don't understand the question.
Sir, what is K here?
K is the ratio between CB and CV.
Okay.
And use it a lot for the equation for BV to power n equal constant, which is referred to BV equal constant this one. This equation is the general one coming for this one, BV to power n equal constant. And this mention for the name for this equation is said bolotropic equation. Bolotropic equation. Okay, bolotropic equation. But when the n equal to gamma or k, gamma is the same meaning of k, and what's the meaning of whatever k or gamma? This bolotropic index, this adiabatic index, gamma, adiabatic index. Okay. By the way, we can I tell you now the type of the process, because it's not mentioned here. What's the meaning of isothermal process? Isobaric, isoporic,
Temperature.
adiabatic, reversible, isentropic. What's the meaning of isothermal?
Thermal temperature constant.
Same
Temperature constant. Great.
Yeah.
Temperature constant.
Constant.
Yes. And what's the meaning of isobaric?
Pressure constant.
Pressure constant.
Pressure constant. Good. What's the meaning of isoporic?
Volume constant.
Volume constant.
Great. Volume constant. What's the meaning of adiabatic?
Adiabatic is energy constant, I think.
There is no heat loss.
Yeah, there is no heat and
Finish. Adiabatic, it means no heat transfer.
Transfer energy. Yeah, no energy transfer.
Reversible, it means can back to the original point. Isentropic. Isentropic, it is a mix
Entropy is
Entropy
constant.
constant.
adiabatic and reversible. Adiabatic and reversible.
Sir, can you explain again? Isentropic is entropy constant, right?
When isentropic is constant, it means adiabatic and reversible. It's combined.
Oh,
Adiabatic plus reversible, it means isentropic. And what's the meaning of isentropic? Entropy constant.
constant.
Entropy constant.
Sir, what is reversible? Can you explain?
Which one?
Reversible.
Reversible, it means the process it come back again to the origin. If the process is going from 1 to 2, it can back from 2 to 1.
Okay, sir.
Here's the meaning of CB we studied.
Constant volume.
This specific heat for water, this is important actually. Water. And I tell you, for water, CB and CV is the same thing. We don't mention CB and
Yeah,
CV.
because it is liquid.
Okay.
Yes.
We have one C for liquid and solid. So this C for water. C for ice, 2.108. Maybe it's not important.
But sir, specific this CP and CV for steam, will it change? Because
Again,
like, sir, I am getting disturbance again. Yeah. So no, sir. The same in that page. On that page. Yeah. For water and solid, because water is liquid and ice is solid, but water vapor will be in the form of steam, and if it is a superheated steam, then it will behave like a air, like a gas. So in that case, CP and CV will vary. Like there will be a constant pressure and constant volume.
In the part for the steam, sometimes we can assume and apply the part for this area as a gas. We assumed is a gas.
And then we can use specific heat, considering specific heat as a constant pressure and constant volume, right?
A specific heat for the water vapor is only one value also here, as mentioned here. But we can apply, and we can consider CP and CV is the same, but it can consider also a gas, but not ideal gas. If you apply as a gas, it's not ideal gas. It's approximately as a gas.
Okay, sir.
Give me answer, please.
1, 2, 3, 4 laws.
Great.
4 laws.
It's
D 1.41.
Yeah.
I don't hear you.
1.41 D.
Yes, correct. Next.
Boyle's law, that is PV is equals to constant, is applicable to the gas under all ranges of pressure.
Small range of pressure. D.
I'll check that chat. No.
A.
One is mentioned B, yes? Someone mentioned B. Actually, it's B, correct, not A. Joule's law, what is Joule's law? He mentioned here for Joule's law and said to us that thermal energy of ideal gas is a function of absolute temperature only. Again, internal energy of ideal gas is function of absolute temperature only. So U, internal energy, is a function for temperature by. That's it. Consequently for that, H, which is enthalpy, is equal to PV plus U, internal energy plus flow energy. This PV I can substitute by ideal gas. PV is equal what?
NRT.
RT.
NR are constant, PV is also constant, then only T.
Are constant, so is only function of temperature.
Plus U.
And this is by default from the equation, from the Joule law here. This already function of temperature only. So the enthalpy is already what? Function of temperature too. Correct or not? Okay. Here, this is what we already presented for the previous one. Okay. Okay. Check and give me answer, please.
Joule's law, B.
B.
So,
B. Joule's law.
correct.
The same volume of all the gases.
Would represent the
D. Gas characteristic constant.
gas characteristic constant. All agree?
C.
Same.
C. Hello.
Yeah.
Yes, sir.
Answer.
C. Molar weight.
C, molecular weight.
All agree? Also want to share the same. Okay. Finally is correct. It's all the style question.
Open system is one in which C.
C.
E.
Both energy and mass cross the boundaries.
Check please.
According.
D.
Which one?
E. Answer.
Just focus for the last thing.
Pressure remains constant.
Charles law.
Charles law.
That's it.
B, two values of specific heat.
Yes. According to Avogadro's hypothesis, the molecule.
A, the molecular weight of all the gas occupied by the same volume.
Gases. Yes.
A. All agree?
A.
All agree?
The molecular weight of all. Yes, A.
Okay. Correct.
C0.
One. Work done by the expansion. Is correct.
0.
Close to finish the set of theoretical questions.
Dalton's law.
Avogadro's
not
hypothesis.
Avogadro's hypothesis A.
Avogadro's hypothesis is correct. Volumetric analysis and gravimetric analysis, just a small difference between these two is gravimetric analysis to measure quantitative like it's quantitative analysis. It's not qualitative and quantitative. But here, this one is generally as a quantitative chemical analysis. Actually, for volumetric analysis, is measure each concentration for each element by volume concentration, which is mean, for example, I have a mixture, and this mixture like gas analysis for the exhaust, and I can measure this one by volumetric analysis. So I can measure this one. This one is 40%. This one is 25%, and so on. Okay, and so on. This volumetric analysis. So normally we use this volumetric analysis when I know the molecules or the substance I measure. I know this, okay? But just I need to know the percentage and the concentration for each one. But gravimetric analysis, normally we use this one when the substance we don't to know this type of this one. Why? Because volumetric analysis, when I use it 1 liter or describe 1 liter, for example, as a volumetric, 1 liter from the water and 1 liter from the fuel, for example. Both by gravimetric analysis is 1 liter for me. This 1 liter, this 1 liter by volume. But to be aware what is the type for each one should be going to gravimetric analysis. Because gravimetric analysis including inside for this one effect of density, molecular weight. Okay? So it depends exactly for each type of material. So I can, what is the name for each one, the component for each one, and also the percentage for each one. So it depends here not on volume, it depends here on mass. So we have two types. One type is depend on the volume, which is volumetric analysis, and one depend on the mass, is gravimetric analysis.
The relative value of each constituent.
Not volumetric analysis.
Each constituent gases. The relative value of each constituent gases.
In another idea, we have one selection on a chat, but if you have another idea, tell me please. Okay, two different now. You can select one from the first answer and one from the second answer. We select from the first answer multiplied, and we select from the second answer molecular weight. So the correct answer is multiplied by molecular weight. Give me an answer, please. If a gas is heated against the pressure, keeping the volume constant.
C0.
Answer, please.
C0.
0. All agree for this answer?
Volume is constant.
All agree for this answer? Actually, because the system here is constant volume, so the work done is what?
0.
0.
Isolated system is one which?
B. Neither mass
B.
or energy process the boundaries.
B.
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 Correct. Opposites of substances like pressure temperature, their thermodynamic coordinates are
Path functions.
Point functions.
yes, great. Which of the following quantity is not the property of the system?
D. Heat.
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 According to hypothesis, so for a given pressure and temperature, each molecule of a gas
Price volume proportion to molecular weight. For a given pressure. Each one
E occupies same volume.
E.
occupies same volume. Correct. Homogeneous and heterogeneous system, easy definitions and difference between these two. Homogeneous system, when I have different materials, but if we mix it together, we obtain one single phase for this one, same like sugar and water. But heterogeneous system, when we have different substances, and we're going to mix it together, it's still not totally mixed and still have more than one phase, to say whatever, but it's not one phase. Mixture of ice and water form
Heterogeneous.
B.
D.
D. Heterogeneous.
Heterogeneous. It's incorrect. Which one is property of a system?
Pressure and temperature.
All of the above.
All of the above.
E.
Right. Yes.
E.
All is property. On weight basis is
Following parts of what?
volume basis and weight basis. The type of analysis here. Okay. This meaning the type of analysis. It is mass based, weight based.
Parts of oxygen. 21.
A.
21.
B.
No, 21 is correct, but if the question related to volume based, okay, you write note for this one for you. By volume base 21. By mass base 23.
Density. Density.
Specific volume. Intensive property. Heat.
Heat.
No answer? Answer, please.
D. Heat.
Heat.
Okay. Okay. Stop now for question. Going back to the some numerical. Focus deeply for this part for numerical. Very important question coming with small questions, but tricks important with for especially for units and calculators sometimes. First law of thermodynamics. First law of thermodynamics. What's first law of thermodynamics? The meaning of first law of thermodynamics: energy can neither be created or destroyed. So represented this definition into this equation change of internal energy. Change of what? Change of internal energy. Change of internal energy equal Q plus work. Q is heat, work is W is work. W is work. So delta E is equal Q plus W, which is heat plus work. This first law of thermodynamics. Easy. And you will see some question related for this one, numerical and theoretical. Clear? Okay.
Yes. Q, doctor.
Q is heat. The sign for Q or sign of work, it depends on this into the system or out of the system. That's it. Okay. But this equation actually it can't determine the system applicable to happen or not applicable actually. What's that mean? For example, if now you drink a cup of tea, okay, the cup of tea here is hot or not? Hot. So the temperature for the cup of tea is higher than the surrounding one. Surrounding for this system, if I consider the system for the cup of tea. So the surrounding is lower temperature. So by default, heat is transferred from where to where?
From the tea to atmosphere.
From the cup of tea to transfer to surrounding. Does that make sense?
Yes.
If I tell you we need to apply first law of thermodynamics for this case as a regular one, and heat coming from the system from cup of tea going to the surrounding. It's okay. You are going to apply and check the delta E or whatever Q or word and get the answer. This applicable? Yes. But if I come and I tell you, please apply first law of thermodynamics for the system, this system, and this system, it seems like previous one, temperature is hot, but the heat is going from the surrounding to the system, to the cup of tea. At the beginning, this applicable or not? Not applicable.
But what is the work done then?
You tell me the heat is going from surrounding to the system? Yes, to the cup of tea. How come? Energy
right.
from low temperature to hot temperature. No, it is impossible. It's impossible, correct?
Yes.
Not applicable. But I can apply first law of thermodynamics for this case. Yes, you can apply. No problem. Change of delta E equal Q plus work. No problem. Nothing restriction to don't apply for the equation. You apply and you get answer. No problem. Whatever the answer is referred to what, but you get answer. Okay. So first law of thermodynamics alone is not enough. And should be going to what? Second law of thermodynamics. Second law of thermodynamics, it's coming to classify the systems. No, this system applicable, going and proceed. No, this system is not applicable. We can't apply this system. According to the equation for second law of thermodynamics, which is referred totally to the entropy. What is entropy? Entropy by definition or the simple meaning, it is random or disordered. Okay?
Yes.
Entropy, it's coming from anything not coming to the original again. What do you mean? For example, if you have a mixture, but if you have two gases and we have a diaphragm between these two gases, okay. If you remove the diaphragm, what happens for these gases? Is mixed together. when I put the diaphragm back again for the diaphragm and put it gases separately again, normally no. Difficult, so difficult. Why? According to the random of the molecules happen, entropy happen. Entropy happen. I can give you one example for that. Actually, entropy as it is function for what? As an equation, function for what? Actually, entropy is function for heat divided
Disorder. Heat divided by temperature.
by T.
Heat divided by temperature.
Yes, I think so. Just wait. I'll check this one for the people I have. Just I check Q over T or Q over T, but I think so. Q over T. Let's see what that is. Q over T, yes. So if delta system S and delta system S is entropy, this is a symbol for entropy. If the entropy here, change of entropy for the system and plus the change of entropy for the surrounding more than 0, you are in the safe. You are in the normal system, applicable system. Okay? But if this addition less than 0, it means this system, it is impossible, not applicable system. If the addition for these two is less than 0, so we check delta S system, delta S surrounding, what is the value for each one. The value is dependent for the Q. For example, when I tell you the cup of tea, what is the temperature for the cup of tea, and the heat. For example, if the heat is 10 joule, for example, this heat is going in or going out, minus or positive, okay? And calculated each one, depend on the temperature for the cup. For example, if 40 degrees C shall be changed to Kelvin, and also the outside, for example, is 25, shall be changed to Kelvin, and just to check the heat. The heat, for example, if like this, is going from surrounding to the cup of tea, which is impossible, not applicable. When you check this and apply by this equation and check to apply for total, we get it, the delta S total is less than 0, which is referred to is not applicable. Okay? So at the end, first law of thermodynamics is very important, very, very important, but actually, second law of thermodynamics is very important to support first law of thermodynamics, to classify the flow, classify the system, this applicable system or not applicable system. Okay? Here, delta system, when you something, when you study the surrounding. From temperature, one refers to system, one refers to surrounding. So the temperature is different. Okay, but Q is the same value but different sign. Same value and different sign. For example, this here, heat is going in, so it's positive, and going out surrounding means. Okay, small questions, theoretical questions, and at the end we will see some question numerical. First, okay. 5 minutes is more. Just 2 minutes. 2 minutes. You can see me or something like that. Okay, just 2 minutes.
Enthalpy of the process temperature only. So the boiling substance internal enthalpy are the function of temperature only.
Perfect guess.
Yes, perfect guess.
E.
Okay, back. For each of the following substance, the internal energy and the enthalpy are the function of temperature only. We have to answer here in the chat. Correct.
D. Perfect guess. Perfect guess.
Free expansion process.
C. Both A and B.
Great. Throttling process. What is throttling process actually? Throttling process, by definition, as you see here, this pipe like this, and this porous plate. Okay, porous plate like honeycomb. Just plate and including in this plate very narrow holes. So throttling process involves the passage of a higher pressure fluid through a narrow construction. What happened for this after the pressure is passing this narrow holes for this one? The pressure before this porous plate is high, but after this porous plate is low. So the pressure is going to reduce, okay? And the volume increase, the volume increase. This process can be back again if the flow going in other side, the pressure it is increase again? Normally no. So the process is not reversible. The process from 1 to 2, high pressure to low pressure, it's not back again to from low pressure to high pressure again, if passing in backside, correct? So this process is not reversible. Not what? Not reversible. Same like the two gases and in between have a diaphragm and going to mix, and it can't be separate again. So this process is not reversible. Okay, because to be obtain entropy without any change, like ideal case, should be have two things. For this system have two things. What is these two things? This should be reversible system, reversible process, reversible, and second thing, adiabatic. And what's meaning of adiabatic? No heat transfer. This throttling process is adiabatic process. But the problem is what? It is not reversible. So the change of entropy, it is not equal to 0. So this process is not isentropic. Isentropic. I tell you before, isentropic process, it means reversible plus adiabatic. Both reversible and adiabatic. And isentropic also, it means delta S equal to 0. Delta S equal to what? 0. This is isentropic process. Constant entropy. This is what I mean. If a gas vapor is allowed to expand through a very